speaker is another top scientist. He is Italian, but he teaches in Glasgow at the Strathclyde University. He's also an expert on masonry arch bridges, and he will talk about scours, I think. So, Enrico, welcome to Padova. You can start.
Thank you very much, Ivo, for the great introduction. Thanks, Paolo, and to the organizers for inviting me to deliver this presentation among many distinguished colleagues. And I really like the fact there are many people from the industry also attending. This is really a good thing. So I will jump straight to the outline of the presentation because I have many slides I want to share with you. And in this presentation, I will first introduce the problem of bridge scour. And we'll show you some of the main effects of scour on masonry arch bridges. Then I will delve into monitoring approaches for bridges exposed to scour. And finally, I will show you the monitoring system we developed at Strathclyde for some bridges in Scotland. So, bridge scour, for those who are not familiar with it, is the removal of bad material around bridge foundations during heavy floods. It consists of many contributions, like the degradation scour, constriction scour, but the most important one is usually local scour, which results from the obstruction to the river flow posed by bridge piers and abutments, which results in formation of turbulence and erosion of the riverbed material surrounding the foundations. Scour is the main cause of collapse for bridges worldwide, with about 22 collapses of bridges on average recorded in the US due to this phenomenon. In the UK also there are many failures recorded every year, and the same applies also to Italy. And there is an increasing trend apparently of failure due to scour, and this is due to a series of causes. Not clear what is the main driver, but there could be the effect of climate change, the reduced funding allocated to bridge risk mitigation, or also the aging of bridges. The problem of bridge scour seems to be haunting me. When I was in Italy, there was this failure of Rubianello Bridge, which is located not far from my hometown. And then after moving to Scotland, there was another failure of Lamington Viaduct, which is also located very close to my new home in Glasgow. And that failure actually was quite a big problem for Network Rail, because the bridge is located along the main railway line between Glasgow and London, and its closure costed lots of money. So, I've been working on the problem of bridge scour since 2015, when I was a Mercury Fellow at Imperial College London, working together with Professor Macorini and Professor Izudin. And the research challenges I've been working on are the evaluation of vulnerability and risk of bridges exposed to floods and scour, the improvement of current procedures for long-term bridge risk management and rapid response to floods, the development of innovative and low-cost sensing approaches and techniques for monitoring bridges exposed to scour, and the quantification of the benefits of structural F monitoring and managing the bridge scour risk. And obviously, in addressing these challenges, I've collaborated with many academics, but also with many transport agencies and companies. And this is really important when obviously you do such a type of research. And so I would like to acknowledge the contribution to my research from Transport Scotland, Network Rail, National Highways, and many other companies. We produced together this horizon scanning paper a few years ago that describes all the challenges that we are facing towards the goal of improving bridge flood resilience. So now let's move to the problem of the effects of scour on masonry arch bridges. Among the various type of bridges, masonry arch bridges are perhaps the most vulnerable ones, because they are built on shallow foundations and or on timber piles that with time may have rotten or degraded. They are rigid structures that cannot accommodate very well settlements, even though I think some of you may argue that this is not the case. And actually, masonry arch bridges are, after all, quite flexible, especially if lime mortar is used, and they can accommodate settlements. But in any case, you will agree that they are age structures that in many cases exhibit already signs of distress for other causes. And here you see some example of notable bridge failures in the UK and Italy, just very few examples to show what are the common type of failure mechanisms that affect these bridges, where you often see a portion of the upper, the front side of the bridge that collapses, involving also the spandrel wall and part of the fill. Very often you observe rototranslational movements of the pier towards, again, the upstream side of the bridge. Sometimes you also observe lateral movements in the case of lateral scour, which is typical if you have bends in correspondence of the bridge. And so, to summarize, typical collapse mechanisms may be two-dimensional in some cases, and there are many researchers that have worked on this, including Paolo, who organized this workshop. Oops, sorry. Yeah, you see, his work on this. But in many cases, the mechanisms are actually much more complex and three-dimensional, and I've been working a lot on this since my time at Imperial. And so I've been working on this by exploiting different strategies for modeling the behavior of the masonry structure and also for describing the soil structure interaction. So in this workshop you will see lots of discussion about different approaches for describing the behavior of masonry components that range from the micro scale to the discrete element modeling. I'm not spending time on this because other presenters will talk more in detail about this. Obviously, when you want to study numerically the effect of scour on the masonry arch bridge, you need somehow also to include a model for soil structure interaction. And there are, again, different approaches that include full 3D modeling of the soil as well as of the superstructure, which is obviously computationally very demanding. But also you can resort to simplified macro elements for describing the soil structure interaction, which could include also a very simple Winkler type of approach. So the first bridge that I studied 8 years ago was Copley Bridge, a bridge located in Yorkshire that collapsed during the Boxing Day flood in 2015. And the collapse mechanism of this bridge is a manual-like failure, where you see basically the translation and the rotation of the piers towards the upstream side of the river that obviously results in the formation of diagonal cracks also in the barrel up to the deck. And we have studied this together with Professor Macorini by using a mesoscale approach for describing the masonry components, which basically consists in using a series of solid elements for describing each brick, and zero thickness interfaces that describe the interaction of the bricks through the mortar joints, and also the possibility of cracking within the blocks or bricks. And for describing the problem of the effect of scour, we resorted to a Winkler type of approach for soil structure interaction. So you have a series of springs surrounding the foundation, and scour is simulated basically by removing those springs that fall inside the scour hole. In a time history analysis, basically, with a staged approach, these springs are progressively removed. And this approach is very convenient because not only allows, in a simple way, to capture the loss of support due to the erosion of the riverbed around the foundations, but also captures naturally the settlements induced by scour on the superstructure. And so, with this type of modeling, we were able to simulate the collapse mechanism of Copley Bridge. Here you see the response for increasing the level of the scour depth until there is a significant rotation of the pier accompanied by vertical settlements and formation of cracks in the pier, and also these diagonal cracks in correspondence of the deck that resemble or are quite close to the cracks that were observed in the real bridge. And very important is this plot here. This shows the evolution of the vertical settlements, the vertical displacement at different points of the structure for increasing level of scour. And this relates a lot to the previous presentation. It shows that for low level of scour, until the scour hole reaches the base of the foundation, you cannot almost not notice anything in terms of response. And then all in the sudden, when you start to undermine the foundation from below, for small increases of scour, you observe a very sudden increase of the response. So this is a displacement response, but if you monitor the crack opening, or you monitor plastic deformation, if you use a model in Abacus, or other response parameters such as rotations, you will observe very similar trends. And this has very important implication for monitoring of masonry arch bridges, because it shows you that masonry arch bridges don't exhibit any sign of warning of a critical situation until it's quite too late, and small increases of scour result in a very critical condition. And second study that we did together with Fabrizio Scozzese and Professor Dall'Asta, he will describe more in detail this study later, is the analysis of the collapse of Rubianello Bridge, the bridge located close to my hometown in Marche, Italy. And for this study, we used a model developed in Abacus with an homogenized approach for the masonry components, calibrated and validated against experimental model analysis results carried out by placing some accelerometers on the remaining bridge portion, and also the model was calibrated by carrying out some flat jack test again on the remaining portion of the bridge. Here you see some comparison between experimental and numerical model analysis results. And we simulated the scour by, again, removing the Winkler type of springs around the bridge, the foundation of this pier, where a scour initiating, triggering the collapse of several spans of the bridge. And again, you see the behavior I was talking about earlier. Here you see the plastic deformations in the spandrel wall. On the right you see vertical displacements. And you observe that there is almost no effect until a scour hole starts to undermine the base of the foundation. And then, all in the sudden, the bridge approaches a critical condition. And this critical condition is attained for this specific bridge for about 1/3 of the foundation being undermined at the base. This is a more recent study, not published yet, but here we tried also to evaluate the effect of scour on the capacity of the bridge against traffic loading. And so we simulated different schemes for describing the load of the traffic. And again, very similar response. For level of scour of the order of 0.2, which means that only 20% of the foundation is undermined. 15%. The load carrying capacity against traffic is almost not reduced. And then all of a sudden, you have this cliff edge effect and a sudden drop of capacity for small increasing levels of scour, which is very worrying. It means that it would be very challenging to provide warnings about an incipient collapse if a scour is occurring. And then this is a more recent unpublished study that we did for National Highways, which is the biggest highways operator in the UK. They needed to have an idea what were the most critical geometrical configuration of masonry arch bridges that could fail due to scour in order to prioritize risk mitigation interventions. And so we resorted here to Istra Bridges, the software developed by Professor Callio, because it has a very nice preprocessor and it was possible to generate models very quickly. So we ran a series of analyses for different types of models, observing the changes in the load multiplier. This is the multiplier of the self-weight for increasing level of the foundation undermined by scour. And again, you see this drop in capacity that, and you notice that failure occurs depending on the geometry of the bridge for levels, for portion of the foundation that are scoured by about 1/3 to half of it. Obviously, half the foundation depth is a limit from a geotechnical point of view if you want to satisfy equilibrium. And now, having done this, overview of the behavior of masonry arch bridges against scour, I will move more towards the topic of this presentation, which is on monitoring approaches. And stepping back a bit, I want to present here the alternative approaches that are available for monitoring scour bridges. And they are usually divided into categories. On the left, you see direct approaches, which mean that you directly measure scour at a location or in an area, and different approaches can be used. They can be ground penetrating radars or sonars, magnetic sliding collars, float-out devices, or scour probes, as you will see later. But then there are also indirect approaches which measure the effect of scour on the superstructure in terms of, for example, displacements at deck level, or rotations, or change in vibration frequency due to scour. And Strathclyde, we have developed a monitoring system using scour probes. These were commercially available sensors used in agriculture for evaluating the depth of water in soils, but they've been repurposed for measuring locally scour. This is in collaboration with Professor Daniele Zonta. And basically, the scour probe includes a series of sensors that measure the dielectric permittivity of the medium surrounding the sensor. And since water, air, and soil present very different values of the dielectric permittivity, it is possible to distinguish between them, and it is possible with a scour probe to detect the depth of scour, but also the water level that led to that level of scour. And we installed a few years ago 2 scour probes at a masonry arch bridge located near Glasgow. One probe was installed in front of a pier, measuring the total scour, which is the sum of all the possible contribution of scour. A second probe was installed at a pedestrian bridge located just upstream of this bridge, and this measured only the degradation of the riverbed due to general scour and a bit of contraction of scour. These sensors have provided continuous measurement of the water level and of scour over the years, with some interruptions due to COVID and the problem in replacing the batteries. Nevertheless, they detected only a minor level of scour of 20 centimeters under a relatively mild flow level, and we were able to validate this measurement by going to site and using a probe, so to manually evaluate the change in riverbed depth. And so, yeah, the probe seems to work fine. However, it is quite expensive to maintain them. You see, they require a very big scaffolding to be installed. This is mainly for accessibility and health and safety issues than for other reasons. However, you can imagine that this scaffolding can attract debris, which is a killer, and it can exacerbate the problem of scour. So I'm personally not a big fan of these scour probes, even though we are going to install more of them at 2 other nice listed bridges south of Glasgow. And I'm quite excited by the installation of the probe at this bridge, Old Bridge, that will take place hopefully next week. Because at this bridge we know for sure that there is a continuous evolution of the riverbed, and particularly there is a live bed scour with redeposition of sediments after having floods. And so when we are going to install the scour probe in front of the pier, we're also going to refill the scour hole. This will be a way to validate the measurement of the scour probe, and also we'll make sure that during the unavoidable extreme weather event that batter Scotland, there will be some scour, and we will be able to detect it. So as I said, I'm not a very big fan of these scour probes, because also they provide only a very local measurement of scour, and for the other issues I listed earlier. And so we are exploring, together with Marie Curie Fellow Eleonora Perugini, alternative approaches for remote monitoring of the river flow properties and scour at bridges. And among these, there are very low-cost ultrasonic transducers for level monitoring. And then we have installed a few cameras at the bridges pointing towards the river, record the videos, and through particle image velocimetry analysis, we are able to map the surface flow field. We also going to test and trial in a new project alternative radar sensors for flow depth and velocity measurement. And also we've been using sonars and fish finders, those tools used by fishermen for detecting the presence of fish in lakes. They're very cheap, cost 200 pounds, but they're very effective in scanning bathymetry and also can be used as scour monitoring devices. But when we had the information only on the surface of the water, so water depth and velocity, obviously we need to complement this information with some modeling for inferring scour at the riverbed. And so we are resorting to either hydraulic models, advanced hydraulic models, such as the one developed by colleagues of mine, Pizarro and Oscar Link in Chile. But also we are exploring machine learning based of approaches, and we have access to a large database of scour measurement for many bridges in the US, and we are going to exploit this to calibrate a better formula for scour, for field analysis. So there is this combination of data from sensors and data from modeling that together will provide temporal estimates of the temporal evolution of a scour, obviously with associated confidence levels. And then we've done some work over the years on exploiting vibration and testing vibration-based monitoring approaches for bridge scour. This is a European project, a CETA project I led a few years ago. We accessed to the raw Proteus facility, this prototype located in Thessaloniki. We artificially induced the scour by excavating below it and measured the changes in the frequency of vibration of the structure through accelerometers mounted at the top. And what we noticed is that for this structure there is a linear reduction of the frequency for increasing levels, portions of the foundation undermined by scour, and when 1/4 of the foundation is undermined, there is a reduction of the frequency of 20%. Obviously, this structure is very far from a masonry arch bridge, but this research was useful for us to get an idea of what are the expected level of reduction of frequency due to scour. And also, numerically with Scozzese, we have been looking at the changes in vibration frequency expected in Rubianello Bridge, in the intact bridge, due to scour. And here you see the comparison of the normalized vibration frequency, normalized with respect to zero scour, for increasing level of the portion of the foundation undermined by scour. Orange curve is Europroteus, so the system I showed you earlier, tested in Thessaloniki, and below is the numerical estimate from Rubianello Bridge. And you see that there is a higher sensitivity of the masonry arch bridge to scour, but this is expected because scour not only undermines the foundations and reduces the stiffness of the foundation, but also induces damage and cracking in the superstructure, which is not the case of this prototype here that behaves almost rigidly under the effect of scour. And we carried out other studies not exactly related to masonry arch bridges, but very recently we performed some experimental tests at the nice facility, new facility in Bristol. Unfortunately, we couldn't test a prototype, a scale prototype of a masonry arch bridge due to the challenges in scaling masonry and developing scaled model of masonry, and so we consider this type of structure in the test. And finally, in the last few slides, I want to discuss a bit about the monitoring system we developed at University of Strathclyde with Professor Zonta. And the premise, the rationale behind this system is that deploying scour sensors at every bridge location is economically unsustainable. It's really unreasonable. You cannot convince agencies to do this. They don't have money, and they don't want to maintain these sensors. So the idea here is to install a few sensors only at critical locations, and then exploit some modeling in order to transfer the information from the monitor locations to the unmonitored ones. And for this purpose, we used a probabilistic approach called Bayesian networks in order to transfer the learning from the monitor locations to the unmonitored ones. So here you see the graphical representation of the so-called Bayesian network that describe the connection, the relationship between the various deterministic random variables involved in the problem. So you have the flow discharge, the water level, and from this descend the contraction scour, and then here is the variables that describe the scour at pier 1 of the bridge New Cannock, and on the right the scour at the pier 2. And the Bayesian network basically makes explicit the relationship between the various variables, and by introducing an observation of a scour at this location, it is possible somehow to infer and update the probabilistic distribution of scour at the location that is not directly monitored, exploiting this correlation structure. And so here you see the result of the application of the Bayesian network to this specific problem. We enter with the knowledge of scour from the scour probe located at pier 1, and then starting from a very uncertain distribution of scour at pier 2, we are able, exploiting this structure here, the correlation between scour at the two piers, we are able to reduce a lot the uncertainty in the knowledge of scour at the pier that is not directly monitored. And to explain a bit the sense behind this, it's reasonable to expect a good correlation between a scour and one pier and the other, because the piers have the same geometry, they are located on the same river bed, and they are located along, exposed to the same river properties in most of the cases, unless you are in bend scour, in a bend. And also, very important, here we are introducing a series of models characterized also by uncertainty, epistemic uncertainty, because particularly the scour formula are characterized by lots of bias and uncertainty. And therefore, introducing the measurement from scour at one location, we can update easily and reduce uncertainty at the other location. We have further extended the Bayesian network to include more bridges located along the same river, and obtained good results in terms of uncertainty reduction. And this has prompted us.
We have to go to the conclusion.
Yes, I jump to the conclusion, so skip this part. And the extension of the Bayesian network to include also measurements from inclinometers and deck deflections. And this can be a tool also for defining optimal strategies for monitoring the bridge, and particularly scour. So basically I reached the conclusion of the presentation. Long list of articles I published over the year on this topic with many of the colleagues that are also present here. And I also would like to acknowledge the contribution from a series of funders that made this research possible. Thank you very much for your attention.